Okay, well, it's a great pleasure to be able to speak at this meeting for Jean-Michel. And this is work I'll report on with Chris Kotka, who's here, if you want to get a more direct version of the story. So this basically arose as an effort. I was interested around about a year ago. I thought I would try and study some infinite dimensional partial differential equations. And the most obvious one is this Dirac-Ramond operator, which was discussed by Witten in the 80s already. It's a formal analog of the spin Dirac operator on a spin manifold, but in infinite dimensions. Witten used it to obtain this genus, his genus in elliptic cohomology. There are other related objects in elliptic cohomology from the same time. So the genus itself is well defined, but his derivation through as the index of a differential operator in infinite dimensions has not been justified. And so it seemed an interesting case to try and understand, because it's maybe the most approachable differential operator in infinite dimensions, just as in some sense the Dirac operator in finite dimensions is maybe the easiest elliptic operator. So the problem is, mainly I'll just try and talk about the background of it. I would like to give you results on the Dirac-Ramond operator, but basically we don't have any. Nor I think does anybody else. So the loop space is infinite dimensional. Now it turns out it's one of the nicest infinite dimensional manifolds that you can find, and that's another reason for studying it. So the basic principle I'll try and outline is that what one really is studying here is string structures on the manifold. And so I'll spend some time talking about string structures on manifolds, and essentially what I'll do today is this relationship. So the first problem is to define the Dirac-Ramond operator. There's various steps in this. The first step is the analog of defining the spin structure. Now, and this is the basic principle. This is the theorem that I'll describe at the end, that spin structures on the loop space of a manifold are in one-to-one correspondence with string structures on the manifold. So this was a principle that was understood already in the 80s, but was not realized rigorously and until very recently, and I'll try and explain why. And right at the end, I hope I'll show you what one can maybe try and do about the Dirac-Ramond operator. There's still several steps missing in understanding the Dirac-Ramond operator, but I think we're getting fairly close. Okay, so let me start off with some topology. So what we're interested in here is this tower of structures. And so the basic theorem is a theorem of Whitehead about Lie groups, which I'm just here applying to ON as somehow the basic structure group for the tangent space on a manifold. So throughout I'll take n bigger than or equal to 5, so I don't have to talk about all the things that happen in low dimension. Nothing terribly seriously happens, just things get a little complicated. Okay, so for ON, the Whitehead tower is a sequence of groups. Now, in general, Whitehead showed that there are a sequence of topological groups, which kills successive lowest homotopy groups in the manifold. So here for ON itself is not connected, and so the first step, of course, is quite simple, but I put it in because this is actually very important. This is, as you'll see, of course, the step of orientation. So you can kill pi 0 by looking at SON, the connected component of the identity. Then you have pi 1 equals Z2. There's a little loop, which is basically the rotation in 2 dimensions, which is not contractible, but double, twice it is contractible. To remove this, you introduce the spin double cover of SON, as very well known. So Z2 is the kernel of this group homomorphism from spin to SON. And so spin n is almost the same as SON, except you've killed pi 1. And the next homotopy group is pi 3, which is always there for a finite dimensional Lie group. This is somehow a more substantial object. And so Whitehead says you can kill this as well. So you can find another group, topological group, which maps to spin surjectively, and which has the same homotopy groups as spin, except that pi 3 is missing. And so the null space has to be a KZ2, as you can easily see from the long exact sequence in homotopy. So the first 3 of these, of course, are standard Lie groups. And the fourth one, spin, cannot be a standard Lie group exactly because pi 3 is trivial. So it can't be a Lie group, and it can't really be a finite dimensional smooth object. There are relatively nice constructions of models of string N. Recently, Nicholas and Waldorf have some infinite dimensional Lie group constructions, but they would be very hard to use in doing analysis. Okay, so how is this related to geometry? Well, corresponding to the Whitehead tower, you have standard successive refinement problems for the tangent bundle. So if you just think about the tangent bundle of the manifold, well, you can think of it as an associated bundle. It's easier to think of the principal bundle, the bundle of orthonormal frames. And so this is a principal ON bundle. The first question is, can you refine that principal bundle to a bundle with structure group SON? So these are supposed to be commutative groups of successive principal bundles here. Of course, we know this very well. This is the problem of orientation of the manifold. Can you find a consistent orientation of the tangent bundle? And so it's obstructed, of course, but the obstruction is very well known. It's the first Stiefel-Whitney class. And when it vanishes, Z2 torsor is a fancy way of saying that there are two orientations once you have one. So this is well-known orientation. And the second step is now if you have an oriented manifold, you can ask whether you can cover the principal bundle of special oriented frames by a spin bundle. So this is the question of the existence of a spin structure in the manifold. This is again obstructed, and you see a nice pattern here of a class, a Z2 cohomology class obstructing it, the second Stiefel-Whitney class. Of course, that's a totally false pattern. It's just because the first two obstructions are both Z2. And so the second Stiefel-Whitney class obstructs it. If that vanishes, then there is a spin structure, and the spin structures are in one-to-one correspondence with the cohomology classes on the manifold, Z2 cohomology classes. Then the less familiar case, which is really what I want to talk about here, is this one, is the question, if you already have a spin manifold, so you've already got rid of this stuff, you have a spin manifold, you ask, can you refine it to a string manifold? So one of the problems, of course, and the string theorists were interested in this, who knows why, perhaps they have a good reason, but this has to be big. I mean, this has to be an infinite dimensional bundle. This has to be an infinite dimensional group if it's to be a decent group at all. And so this is going to be very hard to deal with. Topologically, it's not so hard. The obstruction is more or less the same sort of thing as here, and I'll show maybe later on where this comes from if I have time, but the obstruction is half P1, where P1 is the first Pontryagin class. So it's an integral class. Of course, half P1 would therefore not be an integral class, but this is a standard abbreviation for the spin Pontryagin class. So once you have a spin manifold, there's a refinement of the Pontryagin class, twice which is the standard Pontryagin class. And so it's the vanishing of this. For a long time, I think the topologists thought it was the vanishing of P1, but it's actually the vanishing of this refined class that's necessary and sufficient for you to be able to refine the spin bundle, the spin frame bundle, to a string frame bundle. Now, as I say, you still have a finite dimensional manifold, and now you have this very big principal bundle that, in some sense, you want to analyze, like analytic geometric objects associated with it. The problem with that is that very little is known about string, like the representation theory of string or anything reasonable. And so this seems very hard to approach directly. But this is certainly in principle what one wants to do. One wants to understand consequences of string structure. So let me just remind you very briefly about what happens for spin structures. So this is supposed to be just proceeding by analogy. So the main thing about, not orientation and spin. So, okay. So orientation, well, I just wrote down what an orientation is in this slightly unfamiliar form because I want to use it later on. So an orientation is just a map from the orthonormal frame bundle into Z2, which is continuous, hence, of course, as smooth as you like because it's valued in Z2, which takes both values on the fibers. So we'll come back to this later on. That's why I put it in there. The spin structure is a very similar thing, a step up. Instead of being a map into Z2, it's a Z2 bundle over the the oriented orthonormal frame bundle, which restricts to each fiber to be a generator of H1 of a spin. And so the obstruction classes I mentioned before arise from transgression, and I wanted to discuss a little bit about transgression later on. Okay, so this is just to remind you of what happens in the spin cases. So you can think of the orientation as trying to find an O, and the spin structure is trying to find this Z2 bundle with some properties. Now let me just remind you of the consequences of having a spin structure, very standard. Main thing is the Dirac operator. So the Dirac operator comes from, the Dirac operator, not a Dirac operator, comes from Clifford algebra, which gives you a representation of the spin group. And then if you have a spin structure on the manifold, you get an action of the Clifford algebra on the spinor bundle. So this is the bundle associated with the spin representation of the spin group. And so from combining this data, you get an elliptic operator between sections of the spin bundle, which is important for many reasons. One is in the even dimensional case, this bundle has a Z2 grading, and then the index, this is one of the standard consequences of a T-Singer, is the A-hat genus, and this explained the integrality of the A-hat genus, which I think was known already for a spin manifold, but anyway, this gave it a very nice explanation. Of course, there are lots of other applications of the spin Dirac operator in odd dimensions, and in even dimensions to constant curvature and so forth. So one assumes that a good theory of the Dirac-Raymond operator would have similar consequences. The main thing is to try and emulate this construction of the Dirac operator at some level. Okay, so now let me point out about loop manifolds. So this is the main topic of the lecture in some sense, is the differential geometry of loop spaces. So the loop space is a very simple thing. It's just the C-infinity maps, or some class of maps from the circle into the manifold. Now, in fact, it's very important to understand that that's probably not what a string is. That's what a loop is, but a string is probably the equivalence classes of these up to reparameterization. And this is very important, and I want to emphasize this later on. So it's probably the image of a smooth map in the manifold is what a string really is supposed to be. Anyway, you can't deal with that directly because that's horrible. Okay, so, but this is a nice Frechet manifold. So Frechet manifolds have bad reputation, but this is about as nice a Frechet manifold as you can find. And I want to try and convince you, actually, that you could really get used to this. At least I got used to it. It's paracompact. Well, that's not surprising. But this means that you don't have to worry about most topological things. Check cohomology and so forth go through fine. It has Hilbert completions, has a whole lot of Hilbert completions, basically, if you like, corresponding to each level of Sobolev space above around about a half. You need continuity to stop things getting idiotic. But this is the main compactification. It plays a more important role than I'll show you. I'll maybe mention why later on. This is the energy compactification. And this was the space that actually was used in the traditional study of geodesics via the loop space. Okay, so the tangent space, but I'm much more interested in making things very smooth. And so we're really interested in this. But nevertheless, one wants the cruder spaces. So the tangent space, everything proceeds just as you would hope. The tangent space to a loop, so this is just the infinitesimal variations of the loop. You can easily see that's the same as sections of the pullback of the tangent bundle to the loop. If you have an oriented manifold, then this is automatically trivial when pulled back to a circle. And so this space here is the same after trivialization of the bundle as smooth maps from U1 into Rn, or to say n copies of U1. So this manifold, crudely speaking, is modeled on C-infinity functions on the circle. It's an infinite dimensional manifold, basically modeled on that. Well, C-infinity functions are valued in Rn, which is the same thing. And as I say, this is much nicer. A general Frechet manifold is a frightening thing. This is not. Okay, so M is associated, there's a corresponding loop bundle. So if you have on your manifold, you have the principal bundle of oriented frames. Loops in this give you a loop bundle over Lm. So this is actually the same object. This is really the structure bundle of the tangent bundle on the manifold. And so this is a principal bundle for the loop. So you can just imagine this. This is just pointwise. At every point here, this SON is acting on the frame over the corresponding point in the manifold. Okay, so let me just go through the simple case of spin and orientation. So the question is, how are these two things that I've just discussed related, if at all? I've talked about this tower of structures, and then there's the loop manifold. And a priori, there's no relationship between them. But it was known early on that there's a direct relationship between spin structures on the manifold and a notion of orientation on the loop space. Okay, so first of all, pi1 of SON, as I said, is Z2, which means that this has two components, which means that and one of them, the component of the identity, is naturally the loops in spin. You have to think about this for a minute, but you'll see that it is. And so one can ask, in this previous slide here, one can ask whether this principal bundle has a refinement to a bundle which has structure group the identity component of this. So it's an exact analog of the orientation problem for a finite dimensional manifold. And it was realized by Atiyah that the question of whether this has an orientation, which you can just ask in exactly the same way, is there a continuous map from U into Z2, which takes both signs on each fiber, that the existence of such a thing follows from the existence of a spin structure on the manifold. This was Atiyah's observation. The proof is quite simple because, as I said, the spin structure is a Z2 bundle over this bundle over the manifold. If you think about a loop in this, well, you can drag your Z2 bundle around the loop, and since it's a Z2 bundle, it has natural holonomy. You can ask, do you come back to the same point or the opposite one? And so you get, from the spin structure, you get such a map. And indeed, a spin structure on M immediately implies the existence of a loop orientation. So this connection was understood by Atiyah, and so this is through holonomy. So you might think this is simple, but in fact, the true nature of what's going on here wasn't understood until maybe until less than 10 years ago, as I'll say in a minute. So the converse, that a loop orientation implies the existence of a spin structure, is false. So McLaughlin showed, this is again in the early 90s, that this is true provided the manifold is simply connected. In other words, there's almost nothing going on in the topological level you're talking about. So the second thing I wanted to talk about, the notion I wanted to introduce, this was an idea introduced, at least in this context, by Stoltz and Teichner in 2005 in terms of fusion. So this is a property that holonomy has that other things don't have. So if you have a path space, so I now just think about the path space. Instead of the loop space, we have to think about both paths, and so these are paths which have two endpoints. Smooth maps from the interval into M have two endpoints. So we have an evaluation map which takes you from paths to their two endpoints. Perhaps not quite obvious, but this is a fiber bundle. As you vary points in M2, the local behavior of this is the same. So that's fairly easy, rather easy to see. So this is a fiber bundle over M2, and so it's fairly natural to take the fiber product of this space with itself with respect to this map. And so this just means pairs of paths into M which have the same endpoints. Now, of course, if you have pairs of paths in M with the same endpoints, you have this picture, and of course they're both going this way, but you can get a loop by joining them in parameterization, putting them together. You have to, I mean, if you want to stick with the reparameterization, you have to reparameterize the path, but you can get a loop. So this, you get a map from, if you say, for example, pairs of smooth paths. This is one place where the energy space comes in. These are not smooth because of the discontinuities and the derivatives here. Now, this turns out not to be important. I mean, it's important, but not to be serious. But it certainly maps into the energy space. So I won't explain too much about that. It's minor technicalities, but it turns out to be quite simple to explain. Okay, so there's a fusion map, this psi, which just takes two paths which have the same endpoints, joins them into a loop. So this is sort of a nonsense map, except it's exactly the most important thing in the subject. Now, so if you now think of the triple product, so we now have triples of loops with the same endpoints, triples of paths with the same endpoints. Of course, they don't have to be quite the way I'm drawing them. They can go anywhere in the manifold. So the only property is they have the same endpoints. You have three of them. Well, then, and so we're thinking of these, of course, always as oriented. There are three, well, I guess there are six loops you can make out of this, but there are three obvious ones. You can go up here, back there. You can go up here, back there, or you can go up here and back there. And so the third loop is obtained from the second by fusing, as it were, in and out this there and back loop. So there's a relationship, there's a relation between triples of loops given by triples of paths. So the three loops that are made from three paths. So these three maps, it's actually more conventional to use the opposite numbering system, but this is the one I prefer. So these are just the two projections from this to this, meaning you keep the first two, the second two, or the first one and the last one. And from each of these, you can make a loop. And then holonomy has this property. So the holonomy property is obvious if it's holonomy. In other words, whatever you're doing in holonomy, you're sort of going along, keeping things flat. Well, if we're talking about a Z2 bundle, you're just keeping things continuous. If you go along to there, go down to there, come back again, well, you undo your good work. And so the result is that the product of the holonomy of the first two loops is the holonomy of the second. This fusion condition is extremely important. This was introduced, as I say, by Stolz and Teichner. So the point is that on the loop space, this is a condition which makes sense and which in some sense says that the function looks a little bit like it came from the underlying manifold. Okay, and so what Stolz and Teichner showed that is if you take spin structure on manifold, you get loop orientations which satisfy this, and these are in fact in one-to-one correspondence. So you really solve the problem. Ezra. No, a path is a path. There's no disk. There's no paths in the loop space. There shouldn't be paths in the loop. Three paths in the manifold, three loops in the manifold. Okay, that's a relationship. This is a loop orientation is a refinement of this principal bundle to. Well, you know, whether it's the loop orientation on M or on the loop space is a matter of opinion. Yes. I mean it. Yes, I say loop orientation exactly because I make that confusion. So, I mean, people call it an orientation on the loop space, but of course it's not exactly the same as an orientation in the finite dimensional manifold because you're talking about different principal bundle and extensions. It's analogous to it. But, okay, so. Right. So as I say, this is the theorem of Stolz and Teichner that there's a one-to-one correspondence between spin structures on M and, if you like, these orientations. I see this says element. Okay, well, they're objects on LM. Yeah, I don't know. Maybe I'm not consistent, actually. So let me just show you the proof of this, because I can't show you the proofs of the later things. They're all very similar, but of course more so. And this you can actually understand rather easily, and it captures the nature of most of the constructions. So it's, as I say, Atiyah already understood how to go from spin to this. This is holonomy takes you from spin to fusion, to loop orientation. So the reverse regression map, what you've got to do there is you've got to construct from your U here, you've got to construct this Z2 bundle over the oriented frame bundle in order to get a spin structure. But you're constructing a Z2 bundle out of this data, and it's not so hard. What you can do is you just take all the paths in this oriented frame bundle, take a trivial Z2 bundle over that, and we construct a Z2 bundle over the base by taking a quotient action. So we identify these are two paths, these are the two elements in Z2. You identify them. If and only if these two have the same endpoints, and the orientation of one is this U. So now this is the join of these two paths by this process to give you a loop. There should actually be a psi in there, so this is a relation. Now, just because it's a relation, of course, doesn't help you. But a very nice little exercise will show you that this condition here is precisely the condition that this is an equivalence relation. And so, you know, it makes overwhelming sense to have this fusion condition from this point of view. So if it's an equivalence relation, well, this object descends to FSO. It doesn't descend to FSO, of course. It descends, this should have a bracket around it, to the fiber product of this thing with itself. You've got two copies because you've got two ends of path. So this actually turns out this is a simplicial bundle, which means it's a bundle over the fiber product of this with itself, but it really is just the pullback of a bundle from each factor, tensor, inverse on one side, tensored together. So it's just simplicial. It really is a bundle over FSO. So this is the proof, that is the proof of Stolz and Teichner's theorem. Okay, now, and so one can generalize this quite a lot. So we need to generalize it a lot because so far I've just talked about the relationship between the notion of orientation on the loop space and the notion of spin structure on the manifold. But this fusion condition is important, so I'd put this theorem in here because it sort of shows what is powerful about the fusion condition. So I'm not going to explain all of the objects here, but if we look at the standard transgression map, so one way you can think, I didn't write down the map here, but if you think of U1 cross LM, you have a map from U1 cross LM, an evaluation map to M. Namely, if you take a point in the circle and you take a loop, you evaluate the loop at the point, you get a point in the manifold. So you have a map from U1 cross LM to M. This is a standard form of transgression. You can pull back the cohomology from M to this product space, and then you can integrate, formally integrate this as integral cohomology. You can push forward from this factor to get R. That's definitely a seriously missing L there, to get the cohomology on LM. So this is a map from k-dimensional cohomology on M to k-1 dimensional cohomology on LM. And in some sense, this is the relationship between the manifold and the loop space. And if this was an isomorphism, well, I guess the world would have come to an end long ago if this was an isomorphism always. This is not an isomorphism in general. But that's the problem, in some sense. This is not an isomorphism. But what really Stolz and Teichner's idea is that if you add fusion to this, then you can make this into an isomorphism. In other words, you can recover the objects from M by looking at L of M with fusion. And so that's what this theorem is. I haven't told you what fusive check cohomology is because I'd have to go through covering and so forth. But this is just, and I've changed the notation backwards, but we can, if you take check cohomology, you can add the fusion condition into check cohomology on the loop space. You can define corresponding objects. So what we're dealing with here is check cohomology thought of in terms of U1 functions. You can do this over the loop manifold, and then you get a perfectly good regression isomorphism. From this fusive cohomology on LM, you can map back to cohomology on M. This is the transgression map above, and this is a commutative diagram with the top thing being an isomorphism. So in other words, you can recover the cohomology of the manifold on the loop space. This map here is just forgetting the fusion condition. So you're just dropping the fusion condition. This is a forgetting map. And so TG is not an isomorphism, but this map is an isomorphism. Okay, so this principle is really what's supposed to guide you, that if you throw in fusion, then you may be able to do things on the loop space. In some sense, you might say, well, why not do them on the manifold anyway? But as I say, when we come to string structures, the answer is because they're rather ugly. At least I think they are. Some people, I would feel lost if you weren't asking me questions, Ezra, please. No, absolutely none. Very important. Connected, yes. Simply connected, no. No. If there was, if this condition, yeah. So this with simply connected, you don't need the fusion because. So this really, I mean, I didn't say the loop manifold has components corresponding to pi 1, obviously, and you have to have some way of relating the different components. And the fusion condition, you see, I mean, there can be a hole in here. The fusion condition relates different components of the loops, and because of that, it exactly overcomes this problem. It overcomes all the topological problems which occur higher up. So that's why it's okay. So now let me go back to the string structure. So remember, the string structure is supposed to say, well, you have a spin manifold, and you're asking, does it have this refinement where you can replace the spin group by in some sense, a cruder group, which just has pi 3 killed in it. Of course, you can go up even further. The next level up does exist, and a physicist might tell you why it's called 5 brains. I couldn't understand quite why it's called 5-brain structure. But anyway, we're talking about string structures here. So is there a string structure? Well, what Redin a few years ago, I think in his thesis, a student of Stoltz, I think, showed is that if you take string structures, so string structure is a refinement of the principal bundle of spin frames, if you like to think of it that way. So it's equivalence classes of this. Of course, they have to be equivalent in a way that preserves their relationship to F. But anyway, the natural notion of equivalence of string structures gives you an isomorphism to three-dimensional cohomology classes on the total space of the spin frame bundle, which have the property that when restricted to a fiber, they're a given generator of H3 of spin. So because spin has no pi 1 or pi 2, it's 2 connected. H3 is also, H3 is the same as pi 3 is actually Z. And so this is an abstraction problem. So you're asking, if I take the class, or a transgression problem really, if I take this 3 class on the fibers of F, because the fiber of this, of course, looks like spin, and this is an invariant class, so this makes perfectly good sense on F, can I find a class on the whole of F, which when restricted to the fiber gives me this class back? And so this is obstructed by a transgression class, and this is why this half P1 arises. This is exactly the transgression into 4-dimensional cohomology of the base, this class. So if this vanishes, then this is non-empty, and as soon as it's non-empty, it's the same size as H3 of M, because each of those classes lifts up to give you a difference class of these two. Okay, so the string structures themselves are fairly well understood, except that they're ugly. You can make them relatively smooth, but relatively smooth, I think, is perhaps all you can make them. Okay, so now I come to the core construction. This really is probably due to Siegel, I think. But so we have this spin group. So this works more or less for any Lie group. But let's think about spin. We're looking at loops and spin. This is, again, a group, of course, because we multiply in spin. And these groups come with central extensions, which may seem frightening. This is Kac-Moody theory. Well, Kac-Moody theory was the theory of the Lie algebra, also in the 80s. It comes to these, and of course, these really form a circle bundle. So I write it as EL spin, because this is a circle bundle over L spin, because at each point, what we have is this U1. So we have U1 central extensions. They do exist. They each correspond to spin bundles, and this what Waldorf showed was that these central extensions actually, or the basic one, also have the same fusion properties. So because we have L spin, maybe this is a little bit surprising, but because we have L spin, we can think of the same relationship between loops in spin, as I was describing in this picture here. And if you pull back E by these, so this is the analog, an analog of this condition here. So this is the condition for functions, and this is the corresponding condition for circle bundles, or which is the same thing as line bundles, complex line bundles. Now, because this is given by an identification of circle bundles, you need to know that there's a corresponding associativity condition over Z4. So, I mean, there's a compatibility condition. But anyway, so these central extensions are fusion, and they're in one-to-one correspondence, really, again, with H3 of spin. Because that should be, that should be loop spin there, too. Okay, so I'll explain how to construct such a central extension. They're not frightening algebraic things, or no longer are to me anyway. So the Lie algebra was done by Kac-Moody. The full group in a Hilbert space structure was discussed by Graham Siegel. Let me show you a Fréchet manifold definition to show you that there's some determinant bundle in this. There is, of course, lots of index and determinant hiding in here somewhere. So understand why we want to do this. This is supposed to be the analog of the spin extension of SON. So we now have L spin, and this is supposed to be the analog of the spin group for the loops. So how do you construct it? Well, you go back to 1920s and look at the circle, I have values in Cn because I'm thinking about the spin, so this is really supposed to be like the spin representation of spin. And the Hardy projection, just the projection onto the positive Fourier coefficients of a function. So the Hardy space is a subspace of C infinity functions, this function. And if you take, for example, ordinary pseudo-differential operators, if you know what they are, you can project them onto Hardy space, and you get a form of the Toeplitz algebra. Now, because things are in one dimension, this has a miraculous thing, which is the proper Toeplitz algebra. And this Toeplitz algebra has just the 0th order terms in a pseudo-differential operator. So these are the projections of smooth loops in n by n manifolds. In other words, this is just acting by multiplication on U1 valued in Cn. So this is just matrices at each point. But you can project this onto the Hardy space. And then if you add the smoothing operators projected onto the Hardy space, you get an algebra, which is far from obvious a priori. But in higher dimensions, no such thing exists, but in one dimensions, this does. There are no intervening terms. So this is the Toeplitz algebra. And if you take a loop, which is this bit here, project it, which is invertible, project it onto the Hardy space, of course, it's no longer invertible in general. But it's elliptic as a pseudo-differential operator because this is its symbol. And you can work out its index. This was known already in the 1920s to Toeplitz. And the index, I think, is minus the winding number. It might be plus the winding number, but I think it's minus the winding number of the determinant. This was already known to Toeplitz. And actually, the way they considered it was this was an objectionable thing, this index, and they were interested in the case where it vanished. Anyway, so there's, since spin is simply connected, this is 0 on spin, for loops in spin. And so every one of these things in here, where this is an element of the loops in spin, has an invertible projection, invertible perturbation by a smoothing operator. That's what the other half of the index theorem tells you. If the index vanishes, you can perturb it. You can perturb it to be unitary. And so we have this big group of things. These are things in here, in the Toeplitz algebra, which consist of the loops in spin plus smoothing perturbations such that the total thing is unitary. And this is a big group, but not so big. But the kernel of the group, that is the things that correspond to the trivial loop in spin, are just the perturbations of the identity by smoothing operators on the Hardy space. This, for example, is a classifying space for odd K theory, so it's not a bad object. But the point is really that the Fredholm determinant is well defined on this. So this has a smaller subgroup, namely the group of determinant 1 inside here. And this is a normal subgroup in the whole group. And so you can take this group of the big extension modulo the trivial part of the kernel of determinant 1, and you get a circle over L spin. And this is the basic central extension of the loops on spin constructed. So really, in other words, this E is the determinant bundle over loops in spin in this form. And the regularized trace of, I would say, Wojcicki-Gilliman, but it was almost certainly known to Toeplitz, gives you a connection on this circle bundle. So you can actually construct connections and nice things here, and allows you to compute this cocycle, which I don't have time to say. Okay, now, so so there is a central extension. There's a basic central extension, not just a central extension, but the smallest one, which corresponds to a generator of H3 of spin. Okay, so so as I say, the analog of a spin structure on the manifold is a loop spin structure, is a lifting of this to this. So we have a principal bundle, which is L spin. This is just the loops in the spin frame bundle over the manifold. And we're asking, can we add just one more little dimension to it to get this loop spin structure? So if you want to think about this, what it really is, so this is already the L spin bundle. These are the loops in the spin frame bundle. So above any loop in the manifold, there's an exact, you can change one of these to another one by just multiplying by loops and spin. What we're looking for is a circle bundle over this, which when we pull back by the action of loops on spin, has this twisted transformation law, because this is what means that we'll get an action of EL spin over this. So we want to think about this in terms of this circle bundle rather than as a principal bundle, because I have to construct it smoothly. I have to construct it with fusion. I have to know what its behavior. And it's much easier to understand it as a circle bundle with an associativity condition. Okay, and so we demand that this have the fusion condition. So This again makes sense. In fact, there's sort of a double fusion condition. It has to have a fusion isomorphism, and this fusion isomorphism has to be compatible with the fusion structure on L spin that's natural, that I discussed before. So what we're doing is taking the notion of a loop spin structure and making it stronger. We're making it fusion. This is the idea really of Waldorf, to make it fusion. And then we're going to make it even stronger. We're going to demand a lot of smoothness. Most of the people who worked in this subject and didn't before tended to weaken the smoothness notions. I'll try and discuss at the end what this strong notion of smoothness, this litheness is. It's a very natural notion, and together with the fusion property is very strong. Okay, so I am talking right fast. Oh well. So let's now come back to loop and spin structures. So now we come to the theorem. So as I say, if I haven't lost you completely, let me just go back and make sure you understand about this. Where are we here? So right back at the beginning, let's say. I shouldn't do this. It's terrible. I know, I hate it. But what we're doing is this, right at the beginning, okay? So we have this principal frame bundle. Right. And so the question is there a loop spin structure? So this just, let me repeat the statement again, that we have the loops. So we have a spin structure on M. We have a spin structure on M, which is, this is the spin frame bundle on M. We can just take loops on that, and it maps into loops on M. And two loops here are related by a loop in spin. That just follows sort of, as it were, trivially. This is trivial over each loop. And so what we're asking is there a bundle here with a principal spin action which is compatible with this? So this is the notion of a loop spin structure. Can we refine this so that not just the spin group, the loop spin group acts, but this little central extension? So this is only one dimension bigger. This is big. This is just one dimension bigger. So it's not so bad. So McLaughlin showed, this is early 90s, this is before fusion was introduced, that there's a loop spin structure if and only if half P1 vanishes, but this is under strong assumptions on M, namely that M is too connected, which is not very happy. Waldorf, much more recently, like last year, showed that there's a fusive topological, so not very smooth loop spin structure under the same condition, if and only half P1 vanishes. So what you want is this stronger statement that loop spin structures with additional conditions. So, of course, if you impose more and more conditions on your loop spin structure, then you're getting a stronger theorem, as long as you can prove they exist. So we have this fusion condition. The fusive really also includes strong regularity and another condition that I'll mention in a minute, namely this reparameterization invariance, which is probably very important. We don't really know. Okay, so there's an obvious notion of fusion preserving isomorphism, and these are in one-to-one correspondence with CF, which is the same class of three-dimensional cohomology classes, same three-dimensional cohomology classes as the spin structures. So this says that fusive loop spin structures up to obvious isomorphism are in one-to-one correspondence with string structures on the manifold. And so the idea, therefore, is that you can, in fact, do analysis on this. And so the important part is that these are smoother than these. Not only that, of course, they're infinite dimensional, but there's a sense in which the dimension, the fact that this is infinite dimensional, this is infinite dimensional, they're all sort of the same infinite dimensional space. Whereas for the string structures, the base is small and the fiber is enormous. And so it seems a lot easier to do analysis on the loop spin structure. Okay, so as I said, it's highly desirable, and the reason this paper has not yet appeared on arXiv is that we haven't quite succeeded in doing it, although I was dreaming last night, but we'll see, that we want reparameterization equivariance as well. So reparameterization equivariance means that we have an action on loops by reparameterization of the circle. You want to lift this to an action on this loop spin structure with appropriate, with fairly obvious properties. This seems to be very important. One reason is that sitting inside here, the oriented diffeomorphisms of the circle is the group of rotations. Of course, this, whilst it's a very large group, this is basically the same size as the loops into the circle. This is contractible to U1. So Witten's genus is normally interpreted as the U1 equivariant index, form, where you have to insert formal between every word here. The formal index of the formal Dirac operator, but it's interpreted as a U1 equivariant index, and it's a formal power series. But Brzezinski suggested that probably if you really want to interpret this, you certainly need to go through some form of elliptic cohomology. And that probably there's a relationship that nobody has found between this equivariance and elliptic cohomology. So, what Brzezinski was actually suggesting is that if over the loop space you take some class of infinite dimensional bundles, and these would be probably, if you want to think in terms of principal bundles, these would probably be principal bundles associated with extensions of the loops in UN and probably fusion and equivariance under loops, then this probably gives you a realization of elliptic cohomology. That was Brzezinski hoped and wrote some down. Anyway, so this is the final. So this is step 0 in the program of understanding the Dirac-Raymond operator. At least we now understand the spin structures, and we can find at least the objects on which this is defined. The reparameterization invariance is unfortunate. The problem with this, I haven't talked very much about analysis on the loop space. Let me mention Lie smoothness. But it's a paracompact manifold, and so we have partitions of unity, and you have pretty decent partitions of unity. But what you would really like is partitions of unity which were invariant under reparameterization, and I don't believe anyone knows how to construct them. If you could do that, then I could prove this theorem. We could prove this theorem in a few lines. Well, in a more straightforward way. We have a rather roundabout proof that I'll mention a little bit of as I have time. It's not. I think it's a natural proof, but a lot of the work has to do with trying to get reparameterization invariance. So let me just mention this business about smoothness. So I said this at the beginning. This is a Fréchet manifold, but Fréchet manifolds are generally ugly, and this is a very nice Fréchet manifold. So smoothness on a Fréchet manifold is a somewhat weak notion because if you think about it, if you have a once differentiable function on this manifold, well, it means the derivative exists and is a linear function on the tangent space at each point. That tangent space at each point on a Fréchet manifold should be the model Fréchet space. And for this model Fréchet space is this. So what you've got is a continuous linear functional on this. Well, of course, a continuous linear functional on that, don't worry about the n. That's just a distribution, well, actually really a distributional density. And so hidden within any once differentiable function on this Fréchet manifold, you appear to have distributions at every point. And this is somewhat frightening if you're expecting to do the Clifford multiplication. So you're expecting to take this derivative and multiply something else by it. Well, that other thing better be smooth, or you're in very serious trouble for a start. And so you can refine this notion. So you can ask for much more smoothness, and this is what we do by saying litheness. Within the class of distributions, of course, this thing itself sits as a subspace of smooth functions. And so you can ask for functions whose derivative at each point are given by smooth functions on the loop at that point. This is perfectly well defined, and there's high dimensional analogs of it. The high dimensional analog, the high derivatives, are not quite what you'd think, so you have to be a little bit careful. But nevertheless, there's a perfectly well defined notion of infinite differentiability where all the derivatives are, in a certain sense, smooth functions. They can't be smoothing operators, which is what you might think, because that's going too far, but they're smooth functions. And so this means that you then have a chance of multiplying things. So it's therefore important that the bundles we've been constructing here have this litheness property. For bundles, this means the transition maps have this regularity property. Now, of course, if you had an arbitrary manifold, a Fréchet manifold, this wouldn't make sense. But the coordinate transformations for the loop space are really rather simple objects, because one of the ways of thinking about the coordinate patch on a loop manifold is just, let me draw this picture, is just to take a loop, which of course generally does fairly nasty things, but then look at all the loops which are in a at point S are in a geodesic ball around the base loop at that point. So this is a nice contractible set. It's sort of a tube around the loop, but of course you have to remember that the loop can cross itself. And then the intersection of these two, if you think about what happens, the transition maps between these basic coordinate systems on the loop manifold are just the exponential maps on the manifold pulled back. In other words, not surprising, the coordinate transformations are loops in the coordinate transformations on the manifold. And because of that, the notion of smoothness is preserved. So the coordinate transformations do, in fact, preserve this notion of smoothness, which they otherwise need not do. So, if you like, we have a lithe structure on this Fréchet manifold. Okay, so let me just say a word about the proof of this main theorem before I run. So, what we're trying to do, so one direction is relatively easy. So, in fact, it's the regression direction is quite easy. So if you have because we put lots of conditions on the loop spin structure, it's easy to see such a loop spin structure gives you a 3-class. That's straightforward. Gives you a string structure, if you like. It's straightforward. It's the other way around. Because we put lots of conditions on the loop spin structure, even without them, it becomes hard to construct. And so how do we do it? Well, so what we're trying to do is trying to construct for one of these 3 classes on F, whose restriction to a fiber is the generator of the 3-dimensional cohomology of M, we're trying to construct this loop spin structure. And so what we do is, so this uses the bundle gerbs of Murray in a strong way. So, well, the other direction does. So one thing is that such a 3-class is always represented by a PU bundle, where this is the projective unitary group on a separable Hilbert space. So any integral 3-class always is represented by this. This is just because PU itself is a KZ2. So this is a straightforward theorem. But these are smooth bundles. They can be made smooth over a finite dimensional manifold. And so we have a PU bundle, and the bundle over the loop space on F. So this is a bundle over F, and you can give such a bundle a connection, and then the holonomy of such a bundle. Well, if you think about what it is, I didn't put it up on the board. It's a map, an equivariant map, a PU equivariant map into PU. But because PU has a canonical line bundle over it, circle bundle, this means you can pull that back. And so the holonomy of such a PU bundle is really naturally a circle bundle over the loop space. So that circle bundle is, if you like, is at each point you're pulling back from PU, the canonical circle bundle over PU, by the holonomy of the circle of the PU bundle around that, which is more or less a map into PU, equivariant, actually, but anyway. So we get a bundle C defined from this 3-class over the loop space. The problem is that this bundle has nice properties. It's fusive. It has the fusion condition, but it doesn't have an action of the loops on spin. So this is one of the conundrums here, that this class itself is invariant under the action of spin. All the classes in here are invariant under the action of spin on the principal bundle. But you can't make the principal bundle equivariant with respect to that spin action. If you did, it would descend to a bundle over the base, which would be nonsense. So, so there's a problem here that you do not have the loop spin action on this bundle D. And so the question is how you do that. So I was trying to draw one more picture here. Here's the picture. So we have D. Well, the first thing is you look at the special case of fibers. Let me ignore that. This is the fiber. So you can do things over the fiber, over the paths in fibers of F fairly easily. So on the other hand, what do you do in general? How do you get this action? So over paths that stay in a fiber, you can get the action. Let me just put it that way, and it's relatively straightforward. Now, but over general paths, what do you do? Well, what you do is this. So here's the general path in F, which sort of sits over a path in M. So F is a principal one. So what we do is you take this path and you blip it. So you take at the beginning, and you, because F has a Levi-Civita connection on it, you extend the initial value to be flat. So you extend it to be covariant constant over the loop. So these points here are over the same point in M. Then you have to put in a loop in the fiber to correct, to get back the loop. So what you're really doing is here you're comparing this loop to the two covariant constant paths that start at the initial point and go around to the middle point. And then this loop is the loop in the fiber that comes back at the end to do it. So this is a well-defined map from here into here. This is the blip construction. Oh, okay, so that's all I say about it there. So, and so what we really do is we restrict the bundle to these blipped paths and then pull it back to general paths. The reason these blip paths are nice is that the fiber action on the whole path here is transferred to the action on the vertical part. And on the vertical part, you can identify it with the standard bundle, because these are the fiber paths. And so this is how one uses, maybe it's not, but this blip construction is absolutely fundamental to our construction. Okay, so I only have 2 minutes left to tell you all I know about the Dirac-Raymond operator, which is just about enough time. So anyway, well, no, so there's a spin representation of this. So I haven't had time to talk about it, but there's an analog of the spin. There's an analog of the spin representation of the central extensions of all the Lie groups. Again, you can give a very, very smooth construction of this in terms of the Toeplitz algebra, which I won't try and discuss. But as a result, you do have an analog of the spinor bundle over LM when you have a loop spin structure. And the Dirac-Raymond operator is supposed to act on this. And so we do have one part. Because we've made everything smooth, we have the connection part of the Dirac-Raymond operator. There's no problem with the well, not much problem with the connection part. But what you still need is the Clifford action. And the Clifford action is still needs some work to understand it because, because no one's done it properly in the literature. And so, you know, it's like the rest of it. I didn't really want to do this, but I have to, because otherwise I can't talk about the Dirac-Raymond operator. So this still needs to be defined, to get the Clifford action right, but it looks good. So it looks like that should be soon.